Hello and welcome to the 6th episode of the MEER podcast, a show dedicated to science education focusing on climate change, urban heat adaptation and climate restoration using surface reflection technology. I'm Peter Dynes, a director at MEER, and I'll be the host for this podcast. Today we're happy to have Dr. Ye Tao join us once again to be our educator on this journey. Dr. Tao is the founder and director of MEER, which stands for Mirrors for Earth's Energy Rebalancing. He established this organization to tackle the greatest threat humanity has ever faced, namely climate change. Before setting up MEER, Dr. Tao was running a lab at Harvard's Rowland Institute. MEER is a non-profit organization focusing on surface SRM, solar radiation management, adaptation and mitigation research, as well as climate education, which this podcast is obviously part of. Over time, we'll be discussing everything related to climate reality, feasible mitigation, urban heat adaptation, to the latest scientific papers and ongoing updates with the MEER project. If you have suggested topics you'd like us to cover, you can tweet us at MEER SRM on X, that's MEER SRM, or alternatively contact us through our website meer.org. As I mentioned, the organization is a non-profit and we're currently funded by individual donors. Any donations are always welcome to further our research and humanitarian efforts. You can go to meer.org/donate to contribute. In this episode, we will discuss Dr. Tao's latest trip to China, and we'll also dive into the critical topic of water resources worldwide and how the MEER concept can help to suppress evaporation of our vital water resources. So yes, it's episode 6 of the MEER podcast. We weren't here last month because we had our 3rd year anniversary. We had a video for that actually. If you want to see that, it's on our MEER X Twitter feed. Let's just catch up about where you are, because I know you've since traveled to China, and I just want to know how things are getting on there. I know you were visiting family and whatever, but what's the other goals for the trip there?
I'm currently in the city of Shenzhen, which is very close to Hong Kong. I flew into Guangzhou, which is up north a little bit relative to here. The goals for this trip include visiting some potential collaborators, academics that are experts in evaporation from both land-based systems and lake-based systems, and to consider the possibility of starting formal collaboration, and ideally be able to recruit some graduate students or postdocs to assist in joining our field experiment in Africa. So these are among the major objectives. And of course, I'm also taking this opportunity to visit my parents, whom I have not seen because we're busy getting MEER up and running in the past years.
Yeah, I'm sure you've been away for quite a while. What's the weather and all like in China currently? Is it warm there?
Well, it's a big country, so I can only speak from person from experience in the very southern coast. It's extremely hot. People here also complain about the heat, and people find it difficult to go outside during the day. Luckily for citizens of this country, they have abundant access to energy. So all the indoor spaces, all the buses, all the cars are heavily air conditioned. So you don't really feel or have to be exposed to the heat stress.
Yes.
Temperature here are probably like in the upper 30s with moderately high humidity, comparable to Sierra Leone. But it actually is hotter than Sierra Leone, but it's more comfortable because people get access to AC. So that's the difference for now. I think there's a lot of rain these days, maybe just neighboring places all the way up to even Beijing. I think it just the past few days, rain moved up north. So everything's apparently flooding up there. I think in the coast, it's less of an issue because they are more traditionally exposed to heavy precipitation. Also, it's area prone to be struck by typhoons, hurricanes. So their drainage system is better than up north.
Great. Listen, that all leads us in because this month where the topic is about water. Obviously, it's a very important part of the MEER concept as well. To start this conversation, I want to quote from a recent study published in Nature Geoscience, where they said lakes, which with their rich biodiversity and important ecological services, face a concerning trend. rapidly increasing temperatures. Climate modelers reveal that if the current warming continues until the end of the century, lakes worldwide will likely experience pervasive and unprecedented surface and subsurface warming far outside the normal. Now, we've seen what's going on in Mexico City recently, where they were counting down to day zero and things like that as well. Before, obviously, they had some flooding then, and they've had hurricanes in the country. But can you say what the primary factors are contributing to this global situation in terms of these major droughts?
So I think that there are several issues that you mentioned in your question. There's the questions of why lakes are warming a lot at the surface and at the bottom, and also there's the question of droughts. They're linked in a sense because both the warming and evaporation or drying up of the lakes, they go hand in hand. So let's first talk about say the warming issue. Obviously, the Earth has many different microenvironments in the tropic versus the northern latitudes, the mid latitude, and the Arctics. And lakes in different regions also behave differently. In tropical areas, for instance, lakes don't really freeze over, so they are in liquid phase all year round. Whereas lakes in northern latitudes, Canada, let's say, might be frozen most part of the year. Sometimes maybe it's 3 months, maybe in Maine, it's much longer. So there's this phase change in certain lakes as a function of the local environment that varies depending on where you are on the planet. If we just very simplistically consider the two different states, one is the unfrozen state, and the other is the completely frozen over, where you can skate, where the lake surface can catch snow when it falls. These two surfaces look very different. Let's say we are taking pictures from a hot air balloon or from an airplane. One would appear dark, as in the case of a tropical lake that's completely liquid. The other would appear much brighter or even very white when it's snow covered up north. So right off the bat, these two have very different radiative properties. They interact with sunlight completely differently. In the case of liquid water, they basically absorbs most of the solar radiation as some form of heat, typically up to 95%. Whereas in the case of frozen over lake or when it's covered by snow, it reflects 90% of the sunlight. So they behave almost diametrically different in terms of how they interact with solar incoming energy. So the problem with global warming, or one of the observations, let's say, is that the northern latitude warm faster than southern latitudes, which means that are prone to undergo this biphasic swing between frozen over and exposed states tends to now become totally melted and not frozen anymore for a longer part of the year. So if you count how much energy is converted from the sunlight to heat, in those locations, more of that energy now gets converted into heat. So it's what a albedo feedback. So especially for north latitude, that's also been hypothesized as one of the mechanisms behind the polar amplification, this latitudinal differential warming rate. So it's a positive feedback that makes northern lake systems warming faster than their southern counterparts. Right, but the southern part, southern lakes, they also are undergoing warming, albeit usually at a slower rate because of the lack of this albedo amplification that we just mentioned. So that the warming part that you were talking about, ecosystems have different thermal tolerance properties. Typically speaking, organisms on planet Earth tend to tolerate cold much better than they can tolerate heat. We don't really fully understand why that's both the mechanism of how the basal metabolic rates for many organisms are governed by the environmental temperature because of exponential dependence of molecular processes on temperature is one of the basic fundamental physics activation, chemical activation energy. That's one of the mechanisms that we can hypothesize. But there are also maybe other evolutionary properties because Earth in its history has undergone many glacial, interglacial cycles. So organisms or extents have in its past on 10,000 year timescales experienced such uh, rather dramatic swings in local environments between the current state and half frozen over glacial period, where global temperature is 8 degrees cooler than it currently
Yeah.
is. So maybe organisms, in order to survive these freeze over events relative to current climate, have developed mechanisms to cope with the cold better than coping with the heat. So, given that, organisms that are in tropical environments, which is already very hot, they have relatively very little buffer zone in terms of excess heat that they can tolerate. So even 1 or half a degree increase in tropical regions can really drive individual species or ecosystems out of their thermal tolerance range. That's not the case for polar system or subtropical system,
Yeah.
where in some it's like slight warming, especially in the polar regions, have typically resulted in better performance of both the primary producers.
It's obviously a huge issue. And obviously, evaporation of these lakes and reservoirs is a huge issue as well. If we look at the first 9 days of July in Lake Shasta in California, it was about 2.2 billion gallons of water just vaporized from the lakes. Obviously, MEER is looking at evaporation suppression. Can you explain the concept of evaporation suppression?
Yeah, certainly. So I think everybody can appreciate that when you're making a stew or boiling pasta, you like to close the lid on your pot. And that's to create a physical barrier to prevent the water molecules from escaping. Right? In the end, water molecules are little particles that you really can use a barrier to trap them. And at the molecular level, they more or less behave like ping pong balls. If they have an initial upward velocity by virtue of being expelled from the surface because of the excess thermal agitation, sometimes they can be bounced back. Of course, when they're in the atmosphere, it's different because it's so dense that they make multiple collisions on the way up to the lid. But nevertheless, if you seal off physical pathway for the vapor to exit, you are able to keep the substance within your container. At very simple level, if you consider a lake or reservoir as the opening of your pots, then you can also perform this covering of the surface to prevent physically the leaving of molecules of water, even if the temperature underneath gets warmer. Let's say you use the black plastic to cover the surface. I think it still would function. Because physical barrier
Yes.
effects. Well, that's one approach, which has been in practice in multiple situations. Like in California, I think people tried dump truckloads of these black spheres, creates a barrier that self-assembles in this case that prevents water molecules from leaving. But in that process, the incoming solar energy that's the ultimate driving force for all processes on planet Earth, including evaporation, is not really ejected from the planet's surface, but rather absorbed as heat and transferred convectively to the atmosphere, which will be deposited elsewhere in the climate system. What we are proposing to test at MEER is that we will provide this physical barrier using mirror shooting by virtue of the light reflection properties of the surface. We also prevent the driving energy for evaporation from getting close to the water molecules. And actually, we're trying to eject most of it outside into space so that it doesn't perturb the already overheating atmosphere. So that's the short wave perspective. But we're also hoping to incorporate in our experiments perturbation of the long wave component, because studies on lake evaporation have shown that one potent driver of increasing evaporation in lakes that we are seeing is because sometimes in certain regions it becomes more cloudy, and the clouds are also warmer than they previously were because the air temperature has increased. That leads to an increase in how much long wave radiation, invisible heat that's coming down, striking the lake surface. And they, from the perspective of evaporating water molecules, behave analogously to shortwave for a certain type of water conditions, especially like more turbid, not very visible water in the visible spectrum. Energy. We are also thinking about how we can stop that from coming in by using, say, IR selective material that reflects certain portions of the thermal radiation, but also emits parts of the heat from the lake into space in spectral regions that are not present in the sky.
Yeah.
Basically, we're trying to work on both the physical, like turbulent aspect, material transfer for water, but also the energy flux aspect that drives evaporation.
Yeah, so it's an adaptation and a mitigation at the same time, really. But and in terms of, just to mention those shade balls as well, just so you can clarify, because they have been used. And what's the main, in terms of material input and energy input to make those type of materials? Is there much of a difference in comparison to what we're planning?
So I haven't taken one of these and held them in my hands, but from just the videos you can find online, I think these balls are maybe roughly 6 to 8 inches, maybe 6 inches in diameter. So they're rather massive, and they, based on the way that they roll down the hills, they're probably very dense. So I would suspect it's like the shell-shaped structure, maybe up to quarter inch or some fraction, this fraction of the centimeter in wall thickness. And if that's the, then you probably need like at least 2 or 3 layers of these to create a decent barrier without hole. So if you imagine that you come in with a hydraulic press, and crush a segment of this barrier into a sheet, we're probably talking about on the order of at least 1 centimeter of the material. That's a lot of plastic. Yeah, so just first order estimates, one probably needs 1 centimeter thick of this material in order to realize the specific intervention. And if that's the case, then a 10 by 10 meter squared of the lake would require 1 cubic meter of this plastic. So roughly 1 ton of the plastic. These shade balls, they're roughly like, let's say 6 inches in diameter. And if you look at the videos of how they're dumped into the lake, they fall pretty readily. So they must be decently solid on the inside. Not that they are have a solid core, but they are probably have a pretty thick shell. So if you think about using to cover a lake hermetically sealed so that the water vapor cannot escape readily or have a free line of sight, you probably need at least 2 or 3 layers of this stuff. So if you were to press a layer of this using a hydraulic press or something, squish it into a sheet, we're probably talking about at least 1 centimeter thick of material. So let's say are making a 100 square meter of this material, then you stack 100 sheet, 1 centimeter thick each, and you get a 1 cubic meter stack. That's roughly 1 ton of material. In plastic manufacturing, we're talking typically about 80 gigajoule of energy per cubic meter of material. So that's how much energy that went into making this 10 by 10 meter squared of shade balls. And just for comparison, each ton of glass requires roughly 1/10. I'm making this glass analogy just to show that glass typically is considered high energy intensive material, but even using glass, you can cover 10, 20 times the surface area compared to using this shade ball approach. So
Wow.
the change MEER is trying to implement that should be an advance over the shade ball is that we're using MEER sheeting, which is less than 1/10 of the millimeter. So in terms of material, it's less than 1% material usage, which then directly translates into roughly 1% energy expenditure, because the energy used to blow mold and to coat the sheet is much less than the intrinsic embodied energy in synthesizing the polymers in the first place.
Yeah.
One of the hypotheses we're trying to test in a scaled up experiment, just to see whether from an economic point of view, energy point of view, material availability point of view, there's a change in form factor of what you're using to perform this water interception can make a difference. Does that make sense?
Yeah, absolutely. And we'll come on to that, actually. I just want to ask you, first of all, about the Californian experiment. I wanted to bring you back to that and just to see what you found in that small scale Californian experiment in terms of evaporation suppression and the percentage of coverings and things. What was the findings there?
Yeah, so in that experiment, realistically speaking, it's only a lab scale experiment. And that's typically the first step to test any ideas. You do it at the lab scale before you move it even to any situation that's reminiscent of real world applications. So in that particular one, we used these ice chests as a very easily changed mimic for a small pond system. And the reason why you want to find something, a container, which is thermally insulating on the side, is because in the case of a lake, right, on the length scale of meters, tens of meters, there's essentially closure of heat for lateral transport, more or less speaking. The water is mixing from left to right to left. However they go, the heat content that's in the water when they mix and move around is still contained within the lake. So if you consider the box, 1 by 1 meter of box elements in that environment, if the water is homogeneous, there's no lateral loss of heat. That's why performing this experiment, we chose to buy one of the best ice chests so that there's some very minimal transfer of heat from the inside to the outside through the sides. But the top, of course, we leave open because that's the situation in also real system. The top surface of the water is in contact with the atmosphere. But in these simulated environments, we perform several experiments, which includes different floated surface types and also different aerial coverage. By the same MEER sheeting that we're planning to use the larger scale experiments, we varied shading coverage from 50%, 25%, and also up to 86%. So what we found was that at 85% area coverage, we were able to suppress the evaporation by 65 to 70%. So roughly linearly. So the general result is that the evaporation suppression scales linearly compared to the aerial coverage. And it's a little bit sublinear in the sense that the number we get, the suppression number, is slightly lower than the actual aerial coverage. But that's a phenomenon that's reported in the physics of the evaporation literature. So there's this empirical curve that you can put on the data, which our data also more or less falls on the trend that other researchers have previously found. But actually, our 50% coverage is significantly better than found using other coverage materials, which may be something unique to MEER, but we have not really undertake more detailed mechanistic studies to fully attribute the differences to the various flux, material flux and energy flux mechanism. But the general result that you can achieve order 70% evaporation suppression is encouraging enough for us to consider pursuing further field experiments.
Absolutely. Absolutely. And just quickly on that experiment, was the local animals, were they put off by the mirrors, or?
On the contrary, I think what we observed was that the neighborhood squirrels were especially happy coming to the bins with extensive MEER coverage to drink water.
I think we're going to have to prepare for the bigger experiment, which I'm going to come on to now, actually, in case we've got any herds running through. But yeah, so we're talking about Makini then. So Makini's the second or third city in Sierra Leone, and we've just signed an agreement there with the university. So can you share more details about that collaboration and what are the goals of the bigger experiment and kind of what comparison tests will we be doing?
Yeah, we have been scouting out locations in West Africa to perform this experiment, and we not only considered Sierra Leone but also neighboring countries such as Senegal, which sit slightly more north. So they're in a region of subsidence of the air after the air has dumped all the moisture. So that area is basically bordering the Sahara Desert. In terms of conditions for evaporation, that's actually a better location to do the test if we want to find out, the most contrast, the most difference in evaporation between the control and the perturbation. But there are several other more practical reasons that nudged us to stay in Sierra Leone. One of which is this Saharan dust issue. So that region of the world suffers from dust transport from the Sahara and deposition onto the land. And if we're performing 8 experiments, it would be rather labor intensive for the experimental team to have to clean all the mirrors very often, because in the first experiment, you want to have data that clean in the sense that they tell you exactly the difference on a specific set of conditions for a specific reflectivity of the surface. Obviously, once you have those basic data how the evaporation scales with your activity and also your energy balance differences and actual applications. Of course, we can also use these interventions in the Sahara Desert, also Middle Eastern countries, potentially more dusty. But as a first experiment, just to get the fundamental parameters, it's much better if we can control those parameters more easily and without uh, having to perform a drastic amount of maintenance at all the time.
Yes.
That's the reason was to stay in Sierra Leone, which is less affected by this Saharan dust issue, and also in a region where there's a lot more natural rainfall, so that the natural rainfall can also assist our experimenters in regularly cleaning the mirrors, because that's a phenomenon that we have observed in the urban trial where there's absolutely no labor or manual maintenance needed, because after every rain, the mirror is generated and it's put on.
Yes.
So those are local benefits that we're trying to exploit at the expense of less contrast in how much is expected to happen in a fully unprotected case.
Yes.
So that's we chose McKinney. And McKinney is about 3 hours from Freetown, so it's more inland. It's not as humid, which is good. And it's also the warmer temperature, dry bulb temperature. So those are conditions that's favorable for encouraging evaporation to happen. And frankly speaking, that's probably a condition which is more representative of more other regions of the world that's not immediately next to the desert. Say in Spain or Italy or Sicily or Malta, I think, or Southern Europe in general. I think the condition we're testing would then be more representative.
Yeah.
So those regions we decided to stay in, and also it's like closer to the urban sites, which makes travel easier for some team members, including me myself. We want to be able to contribute and supervise activities on both sites. And the University of Bikini, the UBK, University of Science and Technology, is also pretty ideal site. So apart from the practical issues on dust and evaporation and humidity that we just discussed, the location of the university and the layout of its campus is also quite ideally suited. And the fact that the agriculture department has a lot of activity going on this campus also helps, because the agronomists are really interested in how to get access to water during dry season, finding ways to create new sources of water that help to last the dry season, to extend the cultivation period is of great interest to these agronomists. So they really welcomed us, wanted us really to set up the experiment there. So those are the major reasons why we chose to set up the experiment at BK University of Science.
Yeah, and the other question there was then about what type of comparison tests are you planning?
Oh, I guess most people have already heard by this time floating PV, because obviously one way to put PV fields other than on land is to make use of other artificial surface, including hydrological reservoirs. So we certainly want to compare the different impact of floating MEER field versus floating PV fields. So parameters we wish to investigate include water temperature, evaporation rates, as well as potentially the evolution of different greenhouse gases from the water. Let's say if we can put in controlled amount of biomass to mimic the flooding of like land ecosystems following the construction of a hydroelectric dam, then we can monitor the flux of methane and CO2 from the water, which are driven by bacterial activities, and biology depends on temperature. So let's say if there's a temperature difference in the water based on different covering interventions you're using, then perhaps there's a downstream difference in the rate of greenhouse gas evolution from these space. We're also trying to study different kind of shading material. Of course, the goal is to find the right balance between the efficacy in adaptation and the mitigation. Adaptation being the water retention and also creating favorable conditions for aquaculture potentially, and the adaptation and the mitigation being how much light energy and the IR energy we're able to eject into the atmosphere. So for that, we will be looking at different passive IR cooler surfaces that are able to cool in the 8 to 3 micron atmospheric transparency window. So in total, we're looking at different material types and also different coverage, and
Yes.
potentially from a engineering point of view, different ways to stretch these films and barriers over different size reservoirs. Like we were having this discussion about this shade ball. Obviously, one advantage of the shade ball is that they do not require any additional infrastructure to stay afloat, right? They support themselves and they are sturdy and heavy enough to resist some wind, hopefully. Obviously, we don't have data on that, but they probably resist the breeze.
Yes.
But a 7-micron near film certainly would need some other complementary infrastructure to stay flat, to stay stretched and in place to perform its function. So we'll be also looking at different engineering systems to enable their deployment, stable and safe deployment, and looking for the most durable system, the most economic, and the most ecological system that we can design.
Yes. And I'm assuming bamboo might be part of that as well.
Yeah, bamboo, I think, is one of the primary, like people in different parts of the world have been using bamboo as lumber and also as components for raft. So the fact that they are hollow enable them to float in water naturally. So obviously there are some engineering challenges we need to overcome in order to make them last sufficiently long in water, and also that their potential decomposition or other things doesn't introduce contaminant or other materials into the water, so thus degrading water quality. So there's a lot of engineering and also potential material treatment tests we need to undertake to find what's the most feasible, best way to achieve acceptable performance by all metrics.
Yes, brilliant. I can't wait till the tests begin. Looking forward to seeing what the results are. Just lastly, because obviously we've gone on we're nearly 10 to the hour here. So I just want to quickly touch upon circulation models and global hydrological impacts. So obviously some people would say that if you cover reservoirs and these man-made lakes, etc., with mirrors or reflectors to try and suppress the evaporation in order to save the water resources, they might say you could possibly have an impact on the hydrological systems, and are you going to impact rainfall patterns further downstream from those reservoirs, etc. Can you go into that a little bit more and explain if it would and if it does or if it doesn't?
That's an excellent question, and I think there's different parts to consider to address this concern. I think the most major point that should put people's mind at ease is that the source of water for both marine and land precipitation, the major source of water, comes from the ocean. It's the evaporation from the oceans then transported in the atmosphere that brings clouds, and that eventually becomes rain that ends up on the land. The reason why that's the case is simple. You can appreciate the fact that all major rivers eventually they run into the ocean, right? So if that water didn't come from the ocean, from the land, then eventually very quickly the land would be bone dry, right? So that water has to come from somewhere on Earth, and it's coming from the ocean. So like the vast majority, I have to check, it varies from location to location, but it's safely on the order of 90% of water that contributing to land-based precipitation originate from the ocean. There's some local recycling, but that's the minor part. That's the major point. If you perturb evaporation from the land, it's a small impact to precipitation on land, again, downstream. Second point is that let's say we're doing this perturbation on a freshwater reservoir or hydroelectric dam. The water is just temporarily stored in this upper reservoir. Eventually it goes to power the turbines and eventually gets released downstream. So that water still is provided to the downstream farm. So it's not in the form of evaporated water and some partial precipitation, but it's more directly in terms of downstream water flow. So there is no real impact to the downstream valleys or like drainage system. And there's a third point, which is that why do we need water on land in the first place? So that comes to why do plants need water? The only reason why they need water is during their evolution, they wanted to harness sunlight as energy, and they evolved these pigments in order to absorb sunlight. And they haven't really evolved very well, meaning that a lot of sunlight they absorb is not turned into sugar and energy, but actually converted into waste heat. Plants need to get rid of this waste heat in order to cool down, in order not to burn themselves. So the strategy they found was to grab moisture from the soil, and then by turning this water and moisture they grab from the soil into water vapor, then they cool themselves through this evaporation. So that's the only reason why they need water. And in this MEER adaptation mitigation, what we're doing is we're either preventing the heating of the grass, the foliage in the first place, which obviates the need for water. And we also reduce air temperature, which benefit nearby ecosystems, because when your leaf is intrinsically in lower temperature environment, you have less of the heat load relative to the maximum thermal tolerance range for your particular protein or particular biological structure. So the intrinsic need for water reduces. Right? So by all accounts, there shouldn't be any concern for perturbing evaporation from land. I think reducing evaporation from land would contribute to restoring soil moisture, which helps recharging eventually groundwater, which is globally in a state of depletion.
And just to touch, just because you're talking about evaporation and talking about the oceans as well, just if you were to do large scale, and I know we're going to have Jessica Wan on in a couple of weeks, actually, just on a paper looking at the impacts of this. But if you, in your opinion, if you were to scale marine cloud brightening over the ocean on a massive scale to do mitigation, to do radiation management, would that potentially have an impact on the hydrological cycle?
I think any large scale perturbation you'll perform either by a marine cloud brightening or stratospheric aerosol injection or MEER would necessarily have a large scale circulation impact. The question, is it possible to design the deployment in such a way that creates overwhelmingly favorable results and conditions for all humans? So my current thinking is that the more precisely local you can make the energy balancing radiation, the more handle or not you have relative to tuning this global outcome. In the case of stratospheric aerosol injection, there's very few knob one can tune, because once the particles are released, they become dispersed and circulated around the whole zonal region of the planet. So you have some latitudinal control, but it's more or less the particles smears themselves out uniformly. So there's no spatial selectivity. So you get what you get, right? And that's a major concern. In the case of marine cloud brightening, you face a very similar dilemma, because once you release the aerosols, they become mixed by intrinsic atmospheric transport processes. And generally speaking, you also need to be operating your boats over a significant area in order to have the impact, right? Because there's not really any local benefit or that adaptation benefits to speak of. So all we are seeking is this long range mitigation, thermal mitigation benefit. So, and there's also very selected regions that where you can operate, you have much less control on or latitude or freedom on where you can implement, because some regions already have perpetual clouds and some regions simply do not have the moisture to enable creating more cloud. So you have very small selection of sites where you can perform this. In contrast, when we talk about MEER, we have the whole globe to work with. All the major agricultural regions, all the major ecosystems, and also systems where currently there is no primary production because of either there's too much heat or there's not enough water balance, if not sufficiently in favor of soil moisture. All these locations are where MEER can have an immediate local adaptation benefit. And also, like when you look at like papers in geoengineering and circulation calculations, some of the major output include temperature perturbations and also precipitation perturbation. But people have generally not considered changes to local evapotranspiration, which is the other half of the missing puzzle. Because it doesn't make sense to look at, say, how quickly a person is spending money to know whether the health of their bank account. One also has to look at how much income they have. So both the income and expenditure needs to be looked at. We are assessing a certain pool of whatever it is you're looking at, be it money or soil moisture. So only looking at precipitation is insufficient. to understand the biological, ecological health of the soil, of the moisture in the soil. You also have to look at evapotranspiration. And when you put MEER on farms, on reservoirs, you exert a very strong suppression, 10%, 20%, 50, 70% reduction in evaporation. That's, in most cases, in the vast majority of cases, dramatically overwhelm the slight or the 10% reduction in rainfall in the worst case, large circulation impact scenarios. So I think to a large extent, if the MEER were to be implemented globally, this local drought problem in most regions will be alleviated because the local adaptation benefits overwhelmed is much larger compared to some of the worst precipitation reduction benefit concerns that you have from like previous studies of these geoengineering methods or solar radiation methods.
So I want to finish that up by just mentioning that obviously there was a paper in 2012 and it was concentrating on surface modification in the desert, more or less in the Sahara at scale. And they found obviously that huge albedo modification in that one area had significant impacts on rainfall patterns, etc. And so a lot of people wrote off surface albedo modification because of those findings. But I just wanted you to counter those findings in terms of obviously MEER's plan is not to put mirrors concentrated all in one place.
I think you're asking me about the singular study looking at brightening the Sahara. It makes zero engineering sense to try to do such projects in the Sahara. It's the only type of project that would make sense to do it there would be energy generation. Or if you can get high voltage lines in place for supplying different parts of the more populated locations on the planet in Africa and also in Europe. I don't think this global thermal mitigation makes sense to perform there. And it would be very challenging also to maintain any reflective infrastructure under such like high dust conditions. So I don't see any relevance for that study for MEER, because obviously, as we see from multiple studies in the field, that the result you get is a very sensitive function of where and how you implement the surface brightening or atmospheric brightening method. Mm-hmm. So I don't see that study as having any relevance to the impact of MEER, except for the fact that both, on average, with the lower global average temperature, which is the case there as well, right? So that part the first order impact, we can agree. If you put reflective stuff on the surface of the planet on land, you will lower both regional and global temperatures. Great. But that's using a hammer to do an operation. We know we can do much better than that. So there's no point in dwelling on this very singular, very initial assessment of the primary first order impact, whether it cools the globe or not. Obviously it cools.
Yes, but the
weightlifting question not being properly addressed, except for the 18th paper, Nature Geoscience paper from ETH that looked at albedo enhancement in crop fields by 10%. And they found, yes, we can more or less cancel all remaining global warming if we somehow improve the reflectivity of our crops by 10%. And that MEER can easily achieve. And the precipitation impacts were mostly negligible except for in China. And everybody gets net cooling benefit, no precipitation impacts, except for, I think, southern China, grain producing regions. But once again, those differences has to be taken into account relative to what's happening right now, where there's a huge excess of water that's causing problems. So perhaps maybe that's maybe a welcome. We have a lot of knobs to tune.
Yes.
And it obviously needs to be a global coordinated effort in the end to really optimize conditions, especially for the bread baskets of the world, right? For locations that specialize in tourism, like in Spain, in Greece, okay, let it big, as long as we can get the forest fires under control. If we don't, grow our calories there, we can, tolerate some reduction in rainfall. But in key strategic regions, we need to make sure that we get good water balance, also less extreme weather events, especially, hurricane storms and rain bombs. I think those are what to worry about rather than this 10% change in reduction in precipitation.
Yes, thanks for clarifying that. Yeah, and it's obviously a very complex system.
All right. Thanks for hosting, and everyone enjoy their Sunday, and see you guys at the next podcast.
Okay, so once again, we'll have to leave it there as we come to the end of our time on this podcast. I want to thank Dr. Tao for his time and brilliant insights once again on these very important subjects that we really all need to understand. Hopefully we've all learned something new today. We will hopefully be back again next month, delving deeper into the science and hearing updates on the project. Thanks to everyone who tuned into the live stream and for those listening to this recording. I hope you found the conversation useful and enlightening. Just a reminder, you can follow our developments on our website MEER.org or follow our Twitter feed on MEER at MEER, MEERSRM. And once again, MEER is a non-profit, and we do appreciate any donations you can make towards our ongoing research and humanitarian efforts. To donate, go to MEER.org/donate. Thanks again, and until next time, stay informed, stay engaged. Thanks very much.